Okay, works perfect. So today we are having Andrew Baker from University of Glasgow. So it's a great pleasure to hear what he's going to say. And what we are going to hear is duals of P-algebras and their comodules. So thank you.
Okay, thank you. Well, I'd like to say I've really enjoyed this seminar series. I mean, last year there were lots of Zoom seminars, and I started watching this one, and I found there were a lot of talks I found I was interested in. So it's certainly been a great seminar series, and thank you for the chance to talk in it. What I'm going to talk about is largely algebra, although at the end I'm going to sort of explain a little bit about some of the applications that have been driving me over the last few months. But a lot of what I'm saying is pure algebra. And I should say the main motivation is the Steenrod algebra and various things related to it. So, if you're a topologist and you're familiar with the Steenrod algebra, this is exactly what P-algebras were designed to be about. But it's an area of algebra that personally I think is perhaps not as well known as it should be. And although the original theory was for graded objects, it's possible to write an ungraded version. And I've been trying to do that. I haven't finished yet, but I'm writing a longish document which tries to sort of ungrade this theory. Okay, so what? Oh, sorry, I'm having problems. Let me just, that's better. Yeah. Historically, as far as I know, there's only really one paper by John Moore and Frank Peterson, and it was called nearly Frobenius algebras, which was not a particularly good choice of name. A little bit later, well, 10 years later, Harvey Margolis wrote a big book on the Steenrod algebra, and he, as far as I can see, renamed them P-algebras, because if you know about what a Frobenius algebra is, the graded version is usually called a Poincare algebra or Poincare duality algebra. So I guess what he thought was, it would be better to call these P rather than F, because we're in a graded setting. So if you really want to read about this, Margolis's book on the Steenrod algebra is probably the definitive source. A lot of people have used this technology, but it's not perhaps as well known as it needs to be in topology and maybe outside. So what are these things? Well, okay, we're working over a field, and of course, the Steenrod algebra is a finite field FP, where in my talk, P is going to be 2 in practice, but it could be any prime. So what is a P-algebra? Well, it's a graded cocommutative Hopf algebra. It's meant to be connected, so that means nothing in negative degrees, and in degree 0, it looks like the ground field. By the way, my indexing here is upper notation because I'm thinking of this as kind of cohomological, because I want to think of this as being about the Steenrod algebra ultimately. Later, I'm going to have lower indexing, which is to do with dualizing and homology. Now, in Margolis's book, he doesn't assume these things are finite type, though in practice, those are the interesting ones. So I'm going to put that in as a condition because I think it's perfectly sensible in this context. And it should come to you as a union of finite dimensional sub-Hopf algebras. And these are meant to be a strictly. Now, again, it's not necessary to index on the integers in this way. You can index on a more general partially ordered set, but in this context, particularly with the Steenrod algebra, it's very natural to think of this as indexed on the natural numbers, and these are sort of strictly increasing. Now, these are finite dimensional sub-Hopf algebras, and a basic fact about such things is that they are Poincare duality algebras. They have a kind of Poincare duality pairing, and the top dimension is the dual of the bottom dimension in some sense. Now, if you've ever studied Frobenius algebras or Poincare duality algebras, you'll know that all sorts of things about them are true. For example, free and injective modules are the same, projective modules and flat modules and injective modules are all equivalent. But something like that works for a P-algebra. The basic story that you get for Frobenius algebras or Poincare duality algebras carries over to this setting. These P-algebras, although they're huge things, they're infinite dimensional, they behave as if they were sort of self-dual finite dimensional things from a certain point of view. So here's the first big theorem. If you have a P-algebra, if you think of it over one of these finite dimensional things, remember those finite dimensional things are sitting inside, it's a free module over these. It's also injective as a left or right module. I should perhaps say where that really comes from. Ultimately, what drives that and most of these results is some facts about these finite dimensional things. One fact is that each an plus 1 is a module over an, and it's a free module. That's a basic fact about finite dimensional Hopf algebras. If you have a finite dimensional Hopf algebra, it's free over a sub-Hopf algebra. Of course, Milner and Moore say you don't need finite dimensionality for that, but that's sort of the basic observation there, together with the self-duality, the Poincare duality. Okay, second fact in this theorem is that A is a huge thing. It needn't be a Noetherian algebra. In fact, almost never is a Noetherian algebra, but it is what's called coherent. Now, coherent is a condition that perhaps not everybody has met. You say a module over some ring is coherent if it's finitely generated and every finitely generated submodule is finitely presented. In particular, a ring is coherent if every finitely generated ideal in the left or right sense is finitely presented as a module. So that's a strong condition. It's weaker than Noetherian, but it does have a lot of interesting consequences.
Andy, can I ask a question?
Yeah, sure.
So what is the Poincare algebra in this context? Like, also, should I have an example in mind to understand?
Think of it as Poincare duality means roughly the sort of thing that is true for the cohomology of a compact closed manifold. There's a duality pairing, a non-degenerate pairing, so you multiply and evaluate on the top dimensional form. It's a fact that if, for example, you take the homology over a field of a compact Lie group, because it's a compact closed manifold, it has Poincare duality, but it's also a Hopf algebra. So homology of compact closed connected Lie groups is a sort of prime example of this structure for Hopf algebras. But if you don't require the Hopf structure, just think of compact closed manifold over either F characteristic 2 field or if it's orientable over any field, right?
So we are thinking about these as cohomology, not homology, but
but of course, I mean, the whole point of Poincare duality is that homology and cohomology are kind of isomorphic in a certain standard way. They're isomorphic as modules over the cohomology ring. And of course, homology is really the dual of cohomology. So this is a kind of self-duality statement, really. Yeah. Okay. And then the final statement here is that as a module over itself, either on the left or the right, it's injective over itself. Now, again, this is what Frobenius algebras are all about. So sometimes this is called a quasi-Frobenius algebra, but we're in the graded world, so it's better to think of a slightly different name for that. And that's really what a P-algebra is giving you. Okay. Oh, sorry, the window cleaner is just about to appear at my window. So yeah. All right. So that's the story about this. Now, let me just mention a couple of other things that are quite important. One is that if you have a coherent module over a P-algebra, that means it's finitely presented. It turns out that you can always find an M such that you can think of this as being induced up from a presentation over AM. So essentially, whenever you're working with coherent modules over such a P-algebra, all the action is really going on over some finite AM. So if you, for example, you want to build 3 resolutions of coherent modules, you can sort of think at each stage of working over some finite subalgebra and then inducing up. And that becomes useful if you want to think about homomorphisms between coherent modules. They're basically induced up from homomorphisms over finitely generated AN modules for some N. Now, for example, Bob Bruner has written a lot of software for working with resolutions over the Steenrod algebra, and underlying that is this observation. I mean, that's sort of crucial to working with actual resolutions over the Steenrod algebra. Okay. Now, another fact that's, sorry, I'm not sure I've got the right place here. Another fact that's important is that if you have a coherent module, it actually can be embedded in a finitely generated free module. Free here means possibly with some suspensions. So it's not just copies of A, it may involve shifting of the grading a little bit. And from that statement earlier on, we know that finitely generated free modules are injective. So this is saying that coherent modules embed in injective modules, which are basically free modules, but they're finitely generated free modules, but they happen to also be injective. So this means that a coherent module has an injective resolution of a very nice type. It's at each stage in the injective resolution, you have a finitely generated free module, which also happens to be injective. Now, again, if you've worked with Frobenius algebras, this is a standard fact. And in fact, the proof is just using that. You take your module, you induce it up from a finitely generated AN module for some N. The M0 can then be embedded in a finitely generated free module. Then you just tensor up and you get an embedding of M in a finitely generated free module. But again, that happens to be injective. So that's the way you do things. The reason that works is because A is a flat AN module. You need that flatness to preserve injectivity there. Okay, so this is you're getting some sense as to how you play off the finite part of the picture against the infinite. Okay, now I'm going to call an A module finite if it's finite dimensional over K. This is slightly unfortunate because if you're used to working with rings and modules, you probably are used to the terminology of finite meaning finitely generated. But Margolis in his book uses it in this other sense, and it's very convenient for some of the examples I want to talk about. So an A module is finite if its total dimension is finite. So of course that means only finitely many of the gradings are non-zero. So supposing you have a finite A module M and then some other A module, what about looking at X over A from M into N? So we're mapping from a finite module into some other module. Well, if N is bounded below and free, it turns out that that also means it's injective. That's a consequence of what I said earlier. It's not immediately obvious, but it's true that finitely generated, bounded below free modules are always injective. And therefore, all the higher X groups vanish. So all we're left with is the x0, which is just hom from m into n. And if m is finite, it turns out there aren't any homomorphisms of that type. So x from a finite thing into a bounded below free thing is trivial, right? And secondly, if n is coherent, what is x over a from m to n? Well, again, it's 0. So you see, this is saying that there's a kind of playoff between finite modules and these coherent modules, which are kind of very close to free modules in the sense they have finite presentations and more generally resolutions by finitely generated things. So these are kind of the opposite extremes in some sense. The finite and the coherent modules are the sort of opposite ends of things. Now, these kind of vanishing results are very important for what I'm going to be talking about later, the kind of calculational side of things. These are the kind of basic starting points for calculating X groups. How do you prove things like this? Well, the first part is really an interesting application of the way P-algebras are put together. And rather than perhaps go through what's in the proof, let me just point out that it really hinges on a very important fact about P-algebras, namely that if you take a non-zero element, you can always find a positive degree element so that its product on the left and another positive degree element such that its product on the right, those are non-zero. So, of course, this is not true in a particular AN, but if you work in A, you can always find some elements to multiply up to non-zero things. And if you look at the proof, what you're really doing here is saying, well, okay, if you have a homomorphism from a finite module into A, it must live in some AN because the union of the ANs is the whole of A. So it sits inside an AN, and then basically there must be some element in the image which is killed by everything. But this condition I've mentioned below sort of allows you to, it really comes from the fact in a bigger AN plus 1, you can exploit Poincare duality to find a non-zero product. So there's a sort of playoff there between being inside of a particular AN, and if we go up a bit further, finding something to multiply in a non-trivial way. Okay, so so that sort of result really comes from the Poincare duality property of these finite things. Okay. Now, what about dualizing? Well, okay, anybody who's played with the Steenrod algebra will know that as a ring, as an algebra, it's kind of tricky. It doesn't have a lot of structure. But if you dualize and take the dual Steenrod algebra, what Milner showed was that the dual Steenrod algebra, at least at the prime 2, is a polynomial algebra. At our primes, it's polynomial tensor with exterior. And it's generally much easier to work with a commutative Hopf algebra, in particular one that's polynomial. So dualizing is a good strategy. And in topology, there's been an awful lot of work done in the dual setting, if you want to calculate X groups particularly. So the dual of a P-algebra, I'm going to call a P lower star algebra. This is just the degree-wise dual. You just dualize each degree separately, and then you get a commutative Hopf algebra. And if you have a left A star comodule, it naturally comes with a right A module structure, but you can use the antipode to switch that to a left module structure if you want. So comodules dualize in a simple way to give you modules over A, and we can even work with left modules if you use the antipode. And I'm going to define a comodule to be coherent if its dual in this sense is a coherent A module. Now here's a place where the finite type assumptions are really quite important if you want a precise sort of duality, if you want to go back and forth in both directions, because without that finite type, things tend to get a bit messier. You have to take some kind of completed dual. So I'm going to avoid that. Okay, so I'm switching to working with comodules. And one thing that you can read off from what I've said is that if you have a coherent comodule, its dual has a nice injective resolution. So when you dualize, what that translates to is you can find a resolution which is really a resolution by projective comodules. When you look at A lower star as a comodule over itself, it's a projective object in the comodules. Now, if you've ever played with comodules, you probably have come across the fact that, generally speaking, with big coalgebras, infinite dimensional coalgebras, there aren't usually too many projective objects in the category of comodules. It's very easy to find injective objects, but generally speaking, working with big coalgebras and Hopf algebras, projective comodules don't tend to exist, at least not in abundance. In this setting of P-algebras and their duals, we happen to have a lot of them. This is kind of an unusual situation. So let me just go back up here. So if I just dualize that last result, for example, I can read off some results about, well, okay, my notation here is a bit strange. Because I'm working with comodules and I want to avoid confusion with modules, I'm going to call it cohom to denote comodule homomorphisms, and coext involves derived functors of that, right? Should be fairly clear. So if I just dualize what I said earlier, I get some statements about coext, and in one case, vanishing if my n lower star is bounded below, and co-free, that just means it's a tensor product of A lower star with some big vector space, right? But it has to be bounded below.
Coexit is left derived functor of cohom.
Well, I'm going to say a little bit more about what I mean.
Okay.
Subtlety here about what exactly coext is. I'll come on to that, but it's some kind of derived functor. You know, if you think about what ext is, you fix one of the variables and then derive the other variable. And the way you do that is you take either projective resolutions in the first variable or injective resolutions in the second, right?
Yeah, I'm wondering the cohom here, it is left exact or right exact?
Sorry, what?
Cohom is,
yeah.
I mean, the
for example, you
functor.
fix the first variable.
Yeah.
It's left in the second variable. So you use injective comodule resolutions to compute it.
Okay.
If you fix the right variable, it's a little bit more tricky because you only have projective resolutions for certain modules in the first variable. I'll say more about that.
Okay, thanks.
In fact, this is really a large part of the talk, because what I want to be doing at some stage is computing these coex groups. And I want to sort of use various spectral sequences, and you only get half of them compared to what you get in the world of algebras and modules, because of this fact that there's a slight imbalance in what sort of resolutions you have. So as I said, if you fix the first variable, it's left exact in the second variable, and there are perfectly good injective comodule resolutions. The kind of basic ones are what are called co-free. These are tensors of A lower star with some graded vector space. The problem is projective comodules don't necessarily exist. So it's not really true that this is a kind of balanced functor in the usual sense, right? If you were doing this with ext, it wouldn't really matter which variable you resolved in. But here you have to be a little bit careful about the first variable. Now, one way to sort of make sense of this is by some sort of categorical equivalences. Again, if you're an algebraist and you're not worrying about gradings, if you work with comodules, these give you modules over the dual, but they're not arbitrary. They're what are called they're what are called finite. They're what are called bounded. No, sorry. Locally finite modules. Locally finite means every element is contained in a finite dimensional submodule. But in this graded setting, it's a little bit, you have to be a little bit more careful about what's going on. So if I take the category of comodules, which are bounded below, that's what the flat symbol is supposed to mean. I'm assuming everything is finite type here. Such a comodule gives rise to a finite type module over the dual, which I'm now writing as A upper star. So that's my P-algebra, but I don't get all of them. I get the bounded below ones. I can do something. I can term by term dualize. I can take the graded dual, and that gives me, well, I have to switch variants when I dualize, of course. So this is really a contravariant functor from these special types of modules to their duals, and these are now bounded below finite type things, but I'm in the opposite category. That's because I'm passing to duals, right? In fact, that's an adjunction which makes those categories really correspond, but then I can just embed into the category of all A upper star modules, or rather the opposite category. Now, you see, once I'm in that category, I can think of coext as really being the same as ext over A upper star. But I've kind of gone through some stages to get there. And in particular, I've sort of dodged the difficult issue, which is the lack of projective comodule resolutions, because I know I can form injective resolutions in the category of modules. So I've sort of managed to avoid this issue by passing to a module category. In the world of modules, there are 4 Cartan-Eilenberg spectral sequences for computing, but they sort of depend on different types of resolutions. So let me think a little bit about what sort of Cartan-Eilenberg spectral sequences I can play with here. So let's think about what would happen in the world of modules if I have, well, supposing I have 2 Hopf algebras, R and S, and a map from one to the other, which I'm sort of assuming is injective, and then I can form a kind of quotient Hopf algebra. This is often written with this double slash notation. It has to be what's called normal. This really means that the ideal generated by R inside of S, that the left ideal generated by it should also be ideal. So it's some kind of normality condition. So that if you have a normal sequence of Hopf algebras over a field, and I'm also going to need to assume that S is free over R, which in the graded world is true by Milnor-Moore. And now if I have a left S double slash R module and a left S module, if I want to compute X over S from L to M, there's a Cartan-Eilenberg spectral sequence that has this sort of composite form. There's another spectral sequence if you have an S module and an S double slash R module. This involves putting a Tor in the first variable. Now, the difference between these is that when you set these up as composite functor spectral sequences a la Grothendieck, what you do for the first one is use an injective resolution of M. For the second one, you have to use a projective resolution of M. So, you know, these are set up in different ways depending on injective or projective resolutions. And if you go through setting them up, you ultimately find it relies on some adjunction results for Hom over S being the same as this other complicated Hom, and the second one involves this one. So these are sort of standard toolkit type change of ring spectral sequences, which go back at least to Cartan-Eilenberg, but those are the sort of models for what I'm going to say next. Now, when we try dualizing to comodules, it gets a little bit messier because if you're not familiar with the notation, it's a little bit weird. So the dual version requires another sequence of Hopf algebras. The one in the middle, H, is supposed to surject, and the thing on the left is what's called the, well, it's this K/H business, but it's really, it involves something called the cotensor product, which is the dual construction to the tensor product. I won't write out what it actually is, but it defines a sub-Hopf algebra of H. And again, if you go through, you discover you have some adjunction theorems, adjunction formulae for cohom. Now, this first one, this can also be interpreted as some sort of hom, but for what I'm doing, it's just as easy because K is one of the variables to think of it as a cotensor product. So when you plug in the standard sort of machinery for setting up Grothendieck spectral sequences, you find for a left K/H comodule and a left H comodule, you get a spectral sequence involving this kind of coexed, and inside of it is a cotor, and it converges to coexed over H, right? In particular, in the case where N is a trivial K-module, comodule, I'm sorry. So what happens then? Well, it turns out that the internal cotor sort of peels off. You get something which is really a tensor product of the cotor with two copies of the ground field in and N. And this notation with a wedge is meant to suggest that the comodule structure of that is really kind of involving the coproduct. And if you really want to see what it means, you have to look in terms of the coaction on the tensor product, where you co-opt on the factors and then multiply at the end. So this is kind of dual to what happens when you, for example, look at, you tensor together two representations of a group. You get a sort of diagonal action coming from the Hopf algebra structure in the group ring. This is kind of the dual story for that. So things simplify when the comodule structure on N, the K comodule structure is trivial. And again, that comes up in my calculations. Now, the other thing that you can try to do depends on having some sort of projective resolution of M as a comodule. So this only works, for example, when we're talking about a P-star algebra and a coherent comodule over it. So this is a much more restrictive spectral sequence than you get in the algebra and module story. All right. So, all right. So those are some spectral sequences. Now let's start looking at topology. So, as I said, the prime motivation for this story of P-algebras ultimately was various versions of the Steenrod algebra, and I'm interested in the prime too. So why is the Steenrod algebra a P-algebra? Well, it's a union of finite dimensional sub-Hopf algebras. The nth one is generated by square 1, square 2, up to square 2 to the n. And it turns out that this is always a finite dimensional subalgebra. The first few of them, the dimension of A0 is 2. It's generated by square 1. A1, this has something to do with K-theory. This has dimension 8. Its top dimension is 6. A2, this is to do with topological modular forms. This has dimension 64. Top dimension is 23. And if you want to, if you've never seen this before, you might like to try to work out what the dimension of AN is and what its top dimension is. This is not totally obvious. There are other sub-Hopf algebras and normal quotient algebras, which I'm sort of not particularly going to emphasize, although they do pop up. What about the dual? Well, we know the dual is a nicer object as an algebra. It's polynomial on, well, there are two standard sets of generators, the chi's and the zetas, and these are meant to be related by the antipode. The coproducts have these very simple formulae. If you want to compute the zeta ends in terms of the size, you get this recursive formula. So all of this goes back to Milnor. If you want to understand the dual of AN, it's a quotient of a polynomial algebra. And what you have to do is kill a descending of iterated squares on the first few generators, and then you kill most of the rest. Well, from some point on, you kill the generators. So you basically get a quotient of a polynomial algebra. You can actually ignore most of the generators. It's a finitely generated polynomial modulo some particular sequence of relations. And that's another way of understanding the dimensions I mentioned. Inside of the dual Steenrod algebra, you have this nice family of algebras generated by iterated squares. So if you take the Frobenius endomorphism, ring characteristic 2, so that's just squaring, the image of it is a sub-Hopf algebra. You can square again. So you get this family of sub-Hopf algebras of the dual Steenrod algebra. And the duals of these are quotient Hopf algebras of the Steenrod algebra. And these are all P-algebras and P-star algebras. And then the other family I will mention is if you take the first few generators and raise them to the power 2 to the s, that is a finitely generated algebra. That's also a sub-Hopf algebra. And these have quotients, which are these a to the s double slash things. These are now infinitely generated quotient Hopf algebras. So these are all P-star algebras and dually P algebras. Okay, so let me give you some examples of calculations you can do. And the point really is that at some stage, you use what we were saying about P-star algebras earlier to show that certain X groups, co-X groups vanish. So, of course, the big calculating machinery in stable homotopy theory is some version of the Adams spectral sequence. And in homology, what it looks like, if you want to compute maps from X to Y, what you do is you take the homology of X, the homology of Y, interpret these as comodules over a lower star. The E2 term of a spectral sequence here is this co-X group. So the gradings are, there are two gradings. One, S is a cohomological grading. T is to do with the internal grading on homology. And in some sense, this converges to the maps from X to Y, except that you may want to go from X to a suspension of Y, and that's where you get the grading on these homotopy groups. Now, convergence here, I'm not being very careful about what I mean by convergence there, but loosely, it converges to the homotopy classes of maps from X to Y in some graded sense. All right, so now let's make a completely explicit calculation. Probably a lot of you have heard of the Brown-Peterson spectrum. This is an important object in stable homotopy theory. There's one at each prime. That's a big infinite dimensional object. On the other hand, we could take the sphere, which is a very small thing. Its homology just is one dimensional. So these are both comodules over the dual Steenrod algebra. The homology of BP turns out to be the thing I called A lower star upper 1. It consists of the squares of the homology generators, the xi's or the zetas. On the other hand, the homology of the sphere is just this copy of the ground field. So how would we compute the E2 term of the Adams spectral sequence? Well, we run it through one of these Cartan-Eilenberg spectral sequences, and out pops this E2 term involving co-X to over A lower star upper 1. The first variable is just another copy of that, so that's a kind of co-free object. We've got to compute something with this cotor in it. Now, I'm sort of leaving out the internal gradings here because it's really a tri-graded spectral sequence, but the internal grading I've sort of suppressed at this point. Now, the fact that the left-hand variable is co-free means that actually the higher x groups, co-x groups here are 0. So there's really only the s equals 0 to worry about here. I'm going to come back to this later and show that this actually vanishes. So I'm going to show you how to deduce that from things we know. But basically, if you believe this, what it shows is that this whole co-x group is 0, and that means the U2 term of the atom spectral sequence is 0. And apart from convergence issues, this says there are no non-trivial maps from BP to a sphere. Okay. Now, a whole lot of calculations of this type appeared in Doug Ravenel's very important paper on localization of spectra. In fact, what he showed was that in between the sphere and BP was this infinite family of ring spectra with maps between them. And when you looked at their Bousfield classes, he showed that all these Bousfield classes are strictly different. I won't explain exactly what these x's are. I don't really want to get into that, but basically he did some calculations based on a sequence of Cartan-Eilenberg spectral sequences with change of rings and dualizing to show this. And involved in that, so for example, let's do the case of showing there are no maps from BP to an xn. What do you have to do? You have to look at the atom spectral sequence for mapping BP to xn, and if you work out what that looks like, you end up with this kind of hom, and you end up trying to show it 0, right? Now, in his paper, he kind of glosses over the details of this. So, you know, somehow he has to arrive at this conclusion. So again, I want to sort of explain how you actually prove that, because in his paper, it's a little bit hard to see exactly what's going on in the details. And in fact, there are some issues about whether he's missed some subtle points that need checking. So let's see, I'm going to focus here on the case of n equals 0, because that's maps from BP to a sphere, to show you what you need to do to actually prove that. Now, I think you can't avoid actually investigating the comodule structure on this cotor. I mean, it's tempting to, I mean, in Doug's calculations, it sort of looks like you can sort of essentially ignore the comodule structure and just slide it outside. But I think you really do have to think about it a bit more carefully. So what can we say about this? Well, in fact, to do the calculation, you don't really need the strongest thing. All you really need is a slightly weaker coaction. You can induce a coaction over this quotient Hopf algebra. This is the quotient of A upper 1 by A upper 2. There's a missing star here. So it's enough to pass to a quotient. And the comodule structure there turns out to be fairly simple. This cotor is a well-known algebraic object. This was computed many, many years ago by Milner, actually. And what it looks like is a polynomial algebra on QIs, QK. Each QK is in homological degree 1 and in internal degree 2 to the k plus 1 minus 1. In the bar construction, these things are represented by the zeta k plus 1 elements. Okay, so what is the comodule structure? Well, on QK, you only really get one interesting term. It's psi k squared modulo the fourth powers. So I'm ignoring fourth powers here in this calculation. And the point is that this, if you fix on a homological degree, you actually have a nice finite filtration of this by subcomodules. And this is to do with really the power of Q0 that occurs. So if you think about what's going on in degree T, this is cohomological degree T, you have monomials of total degree at most actually equal to K. So the filtration I'm putting on this, in each cohomological degree, each degree T, the Kth filtration group involves monomials in the Qs where the power of Q0 has this bound on it. And the point about this filtration is when you look at the successive quotients, you've lost the comodule structure. You don't see any coaction because the quotients turn out to be trivial. There's a trivial comodule structure on each successive quotient. Now, how do we use that? Well, the way you use this is to show that if you have a comodule homomorphism from A upper 1 lower star into this, because we have this finite filtration, we can pull it down to some filtration term. So we can sort of push it down as far as we can in this filtration, and let's call the corresponding group K, call it the K0th filtration. So we make that K0 as small as possible. And now what you can do is kill off the lower filtration. And now we're in a comodule which has no coaction. So we can easily push off using a vector space projection into a one-dimensional trivial comodule. And now you can sort of go back and say, well, if that happens, what are we really doing? We're taking this Hopf algebra, which is actually a P lower star comodule, Hopf algebra. We're building a map from something which is actually co-free into a trivial, well, a finite dimensional comodule. But we saw earlier there are no such maps, right? That's a general fact about P star comodules. So this trick with the filtration allows you to deduce that there are no non-trivial comodule maps of this type. And that's what you need to prove, let me just go back. That's what you need to prove that this group here is 0 in the case where n is 0 anyway. So, this is where the P lower star structure really kicks in, because we're mapping into something where a comodule map would be detected by a map into a trivial finite dimensional comodule. Okay. Now, all of that is basically going on in Doug's paper. So let me mention what I've been doing recently. I've been working with the symplectic Bordism Thom spectrum. Now, for those who aren't familiar perhaps with cobordism theories, the classical groups like the orthogonal groups, special orthogonal groups, unitary groups, these all correspond to Thom spectra, which are associated with various cobordism theories. And there's one that sort of stands out a little bit, because whereas complex cobordism and unoriented cobordism and oriented and all these other types of examples were really computed back in the 50s and 60s, the symplectic version is still somewhat mysterious. I mean, it's sort of been determined, its homotopy has been determined in the sense of the atom spectral sequences being computed, but it's still a rather mysterious object in terms of what's really going on in the answer. The interest here is all at the prime 2. At odd primes, it's not terribly exciting. It's just a wedge of BPs. So what was an outstanding question, going back to, I think, the time of Doug's paper in the early 80s, was exactly how does MSP relate to MU and BP in terms of the Bousfield classes? And it's known that there is a relationship, there is this inequality between Bousfield classes. And this comes because there's a ring spectrum map from MSP to BP ultimately. So this is sort of a known statement. The question is it an equality or is it sharp? And what I can prove using this P-star algebra stuff is that in fact, MSP, when you look at its Bousfield class, is strictly between the Bousfield class of the sphere and BP. So what do you need to do to prove these? Well, the strictness for BP follows, I mean, there's a way of proving things like this in Ravenel's paper, which works just as well here, provided you can show that the E2 term of the atom spectral sequence for maps from BP to MSP is 0. So this cox is really the E2 term of an atom spectral sequence. And you're trying to show there are no non-trivial maps from BP to MSP. So you have to somehow run through various change of rings type calculations to see that that's 0. And algebraically, it reduces to showing that this cohom is 0. And again, there's a trick for reducing that to another cohom where you're working with A star upper 1 mod A star upper 2. Basically, it's very similar to what we were talking about earlier. Sorry?
Could you explain what's the bigger than symbol mean here?
What is the
bigger than symbol? S0.
Oh, well, okay.
Yeah,
so this is Bousfield class notation. It means that the MSP acyclics are BP acyclic. And when you have a module spectrum over a ring spectrum, an acyclic for the ring spectrum is acyclic for the module spectrum. But in general, the reverse inequality, the reverse statement is not true. Okay, so if you think of a Bousfield class as all the things which are killed by smashing with the spectrum, it's a statement that being killed by the ring spectrum means it's killed by the module, right? Yeah, that's the way I like to think of it. I mean, Bousfield classes are really best thought of as collections of acyclic spectra over another spectrum. Okay, so ultimately it reduces to this bottom cohom, and this is very much what we earlier, right? So so that vanishes because of the sort of calculations I was doing on the last slide. Now, it turns out that the other implication is a lot more, and in fact, the only way I know to do it involves pushing this whole idea of looking at the kind of cotour that we were talking about earlier, but here you have to take a slightly more exotic one. You have to take A lower star mod the 4th powers and trying to show there are no comodule maps over A star upper 2 from A star upper 2 into this cotour. And that in turn can be reduced to looking at A star upper 2 mod A star upper 3. So this is the 4th powers mod the 8th powers into this cotour. But that cotour is not, I don't think that's computable in a nice way. I don't know what the answer is for that. But I can play around with filtrations in various cunning ways and show that we still have this property that there's a nice finite filtration on this gadget as a comodule over this, not quite the one you might expect, but A star upper 1, that's the squares, mod the 8th powers. So you have to do something a lot more complicated here, but in the end, you get a filtration which is finite, so you can play the same trick to prove that that cohom is 0. Now, what I would love to do here is find a simpler argument, but I simply don't see how to do it without an explicit calculation of this cotour. And I think that is not, certainly not as easy as the one we met before. And, you know, even if you can compute it, you then have to still play around with the comodule structure. And I don't know how easy that would be. So the filtration argument turns out to avoid doing the calculation explicitly. Okay, so Now, I'm not going to read this out because I have no idea how you pronounce it, but that's what I got by Googling. So maybe somebody can tell me how you pronounce it. So,
okay, thank you. Thank you very much, Andy.
thank you.
Yeah, this is pronounced as dinlediğiniz için teşekkürler.
Okay.